Hello and welcome to this video in which I'm going to be going through the AQA GCSE Computer Science Paper 2 Specimen exam. So this exam was made by the exam board to give people an idea of what an actual Paper 2 would look like. This paper wasn't actually sat by anyone because it was released before the course was officially launched. So unfortunately no grade boundaries, but it is a realistic paper on the same topics the real exam will be on and with basically the same structure, written by the same people most likely. So this is really important to try this paper, especially if you're watching this fairly soon when I'm recording it, because there aren't really any past papers available for this current course at the time of me recording this. Of course, down the line there hopefully will be many past papers for you to try. So this video is going to be me going through and answering these questions as if I was doing it in a real exam, but hopefully bringing up some useful tips and misconceptions and just other bits and pieces related to these questions. I am not, doing this sat next to the mark scheme because of course you can look at the mark scheme yourself. That is linked down in the description. So this paper, paper 2, is the more theory paper. Now paper 1, as you might know if you've done it by the point you're watching this, it has got theory too. It's not just programming and writing Python code, say. You have to learn and revise for it. Paper 2 is more typical. A typical exam, you've got to sit down in front of a textbook, in front of my videos, say. There'll be a link to my playlist in the description. Sitting down in front of, BBC Bite Size, whatever you're using to revise, hopefully a combination of a few things. You sit, make notes, do questions, and that should prepare you. There is quite a lot to revise, of course. Make sure you revise every topic. There is a big range of topics to revise, so make sure you revise all of it. Now, I will say in the past, anecdotally, people have done worse in paper 2, which you would think people do worse in paper 1 because it's harder to get ready for paper 1. You still can prepare properly, like I just said, but it's harder to you can't cram it basically, right? Paper 1. Paper 2 you can. I have found people do worse at paper 2 because it comes after paper 1. Usually, paper 1 has been the first ever GCSE exam. People are really hyped up, they spend lots of time on it. By the time you get to paper 2, which in the past has been later in the week or a couple of weeks later, people are a little bit more fatigued and maybe don't spend as long preparing for it. That's even worse if this exam is in the afternoon and you've got an exam like chemistry in the morning, as it is in this year. Of course, that might change in the future, but if you're watching this, weeks and weeks before your exam, please revise paper 2 now, which is kind of what you're doing, I suppose, but put effort into it now because you might find actually when you get to the real exams, your timetable might be so busy that you don't have enough time to revise for this, and actually, if you put the hours in, you can definitely do really well with paper 2. And paper 1, of course, but paper 2 is more straightforward to get ready for, I would say. Anyway, let's not talk any more about that. So this paper is 1 hour 45 minutes, not 2 hours, which is what paper 1 is. Some people might get a shock when they see this. So it's still only worth 90 marks, the same as paper 1. I say only, it's still worth 90 marks, which again, basic exam technique dictates you spend about a minute a mark, which gives you plus 15 minutes to check at the end. In theory, of course, in reality, you might find you're more rushed or finish early, but that's about what you're looking at. So when you're practicing papers like this one in real exam conditions, time yourself, and if you are far ahead or behind this, that is a sign maybe things are not quite how they should be. Just on the other general admin for this, like paper 1, no calculator is required, or you're not allowed one at least, so just be aware of that. Don't bring one in, it will create more stress than it's worth. And make sure you use black ink. That is always, I think, very upsetting for teachers if they hear someone's used blue ink by mistake. Okay, now, starting with question 1. So we're given a bit pattern, and we need to convert this binary into decimal. These are only ever worth a few marks, usually 1 mark for binary decimal conversions, so please don't spend a long time on these. These should be just totally straightforward by the time you get to your real exam. They should be, the easiest questions on the paper. So we've got this non-binary bit pattern. What I would do is add column headings above this number. So let me zoom in really fast so I can do this properly. So the place value for binary starts with 1, like in decimal, then goes to 2, 4, 8, 16, 32, 64, and then 128 is our last one. So when we're going from binary to decimal, all we do is add up the place value headings when there is a 1 underneath. So here I'm going to add up 64, I'm going to add up 8 and 4 and 2. Well, 64 plus 8 is 72, plus 4 is 76, plus 2 is 78, which is our answer. For 1.2, a standard follow-up question, we now need to convert this bit pattern into hexadecimal. Now what you could do is take 78 and convert it using, say, 1 and 16 as your place value, and you divide 78 by 16 and find the remainder, and so on and so on. But the quicker way to do this is, when you're given the binary, is to split the bits, or split the nibbles to be more accurate. So what you should be doing is looking at each nibble. A nibble is 4 bits, and 1 nibble equals 1 hexadecimal digit. So if you split your bit pattern into multiples of nibbles, you convert each one to hexadecimal and put them together, and that gives you the final answer. It's why hex is used, because it can shorten long binary bit patterns. So 0100 in decimal is 4, which in hexadecimal is also 4. So what I might do here, because it looks really confusing, what I might do is add a little subscript after each one to tell me the base. So binary is base 2, decimal is base 10, hexadecimal is base 16. So if you see a little subscript, that's what that means. Now the reason why 4 in hexadecimal is 4 in decimal is because the first 10 digits in hexadecimal are the same as decimal. So 0 to 9 are the same. Then for the final 6, which needs to get 16, we use A to F to represent 10 to 15. Right, the second number, 1110, is 8 plus 4 plus 2 in decimal, which is going to be 14. And in hexadecimal, 14, well, if I said F was 15, therefore E is 14. So all you need to remember is that A is 10 and F is 15, and you can work out what the numbers in between are by just following the alphabet. So final step, you can't leave it like this. Final step is to put together the two nibbles in order. So 4 came first, then we had E. So the answer here is 4E. Now for the third part of question 1. So a student's answer to the question, why is hexadecimal often used instead of binary, is shown. So they said, because it uses fewer digits, it will take up less space in a computer's memory. Explain why the student's answer is incorrect. So this is a really common misconception. It's good that it's been highlighted in an exam question. The reason why it's incorrect is the computer only uses binary. So if I'm storing hexadecimal, really that is not being stored in hexadecimal, it's being stored in binary instead. So no matter what we have on the screen, we are still storing it in binary. So let's say that. So all data is held in memory in binary. So despite hexadecimal looking shorter to us, it will not take up less space. So that's the key idea of hexadecimal, right? It's only for humans. It doesn't affect the computer at all. It makes things easier for us because long binary is hard to remember, easy to make mistakes, and takes up space on our screens, but not within the computer's memory. And then for 1.4, we need to explain how a binary number can be multiplied by 8 by shifting bits. So shifting bits where we add or take away digits from a binary number. Now if we are multiplying, we are adding zeros to the right, which means we're doing a left shift. You know, for example, 10 in binary is 2. If I add a 0 to the right, that then becomes 124. So one left shift is timesing by 2. So if I want to times by 8, I need to therefore do 3 left shifts, because if 1's timesing by 2, 8 is 2 times 2 times 2. So therefore I'm doing 3 left shifts. Now the question does say explain, so let's be super safe and say you can add 3 zeros to the... Now the proper phrase is the least significant end of the bit pattern, because it's least significant because it has the lowest place value. You could just say right hand side of your bit pattern, which is doing 3 left shifts. A right shift divides by 2 each time, but you truncate the number because any ones get lost beyond the binary point. And if you think you might forget your left and right with shifting, just do a quick example like I did and see what it's doing. Okay, 1.5 ASCII, American Standard Code for Information Interchange, is what that stands for. In my exam, that was a question. What does ASCII stand for? And I didn't know it, so make sure you do learn that. So ASCII is a coding system that can be used to represent characters. In ASCII, the character A is represented by the numeric code 65. Shade 1 lozenge to indicate which character is represented by the numeric code 70. So this is testing you on the understanding that ASCII is sequential, meaning the codes follow a natural order. So the code for B is 1 bigger than the code for A, and so on and so on. Now, first thing to say is, the uppercase and lowercase letters are different. They've got different codes. So uppercase A is different to lowercase a. So we can straight away rule out the lowercase ones and also the numbers, because 5 bigger than A, than capital I, A, is not going to be in the number group or the lowercase group. Just between A and B. Well, let's write down the alphabet. So we've got A, B, C, D, E, F, and that's the letters given to us. So if A was 65, B is 66, 67, 68, 69, and 70. So therefore, the answer is F. So this isn't guesswork. You can just use the pattern of the alphabet or the numbers to find the real character corresponding to a particular code. For 1.6, we're told, and we should know this already, but Unicode is an alternative to the ASCII coding system. State 2 advantages of using Unicode to represent characters instead of using ASCII. Well, Unicode is newer because ASCII effectively didn't give us enough characters. The original ASCII only gives 7 bits for each character code, which only leads to 2 to the power 7 combinations, which is 128, which is not enough characters for other languages. So Unicode is much bigger. Unicode's at least 16 bits, which gives us at least about 65,000. So Unicode can represent other characters is one advantage. And really it's a follow-on from this, but it's distinct enough to get you another mark. So therefore Unicode can also represent other languages than English. So other languages than English. Now those 2 points are quite similar. They would both get you marks, but if you were wanting to be more cautious and differentiate your points a bit more, a third one might be the idea that Unicode's much more interoperable. That means it can be used with lots of different programs all over the world. ASCII itself is quite limited because it might not be as easily used across the world, whereas Unicode is used a lot more widely nowadays, no matter really who you're communicating with. Now, I once marked a mock exam where almost everyone in a class I didn't teach wrote down that Unicode was universal. And I think I gave that the mark, benefit of doubt. It was a heavy benefit of doubt. I'm not a big fan of that. You know, people connect that to Unicode, universal. But the point about it being used worldwide is a valid point, which I think is what people meant. So I would avoid using that word, but if you're using the gist that it's used around the world and so is interchangeable and is compatible across the world, that would be a better point to make. Now, when data is stored in a computer, it is often compressed. One method that can be used to compress text data is Huffman coding. To produce a Huffman code, each character in a piece of text is placed in a tree, with its position in the tree determined by how often the character was used in the piece of text. You'll notice a trait of AQA is to explain a lot of the theory in their question papers. I find it a little bit odd, but it's quite a nice thing, I suppose. So, we've got a Huffman tree for the text, Zoe saw a zebra at the zoo, down here. Now, I really like Huffman coding because it seems very difficult and looks very difficult. If you show that to a non-computer scientist, they'll be quite impressed, I would say. But actually, once you understand how these work, it's not very complicated at all, especially in the exam, right? If you were asked to build a Huffman tree in the exam, sure, that would be difficult. But all you are asked is to interpret and occasionally do some calculations with this. So, using this Huffman tree, the Huffman coding for the character E would be the bit pattern 110, because from the top of the tree, E is to the right, then right again, and then left. And Z would be 010, because from the top, Z is to the left, then right, and then left. Okay, again, that's AQA explaining stuff to us, which you should know, actually. So, what was the first one? I wasn't listening to myself. E is 110. So let's see why that's the case. It did tell us, actually. So E is now 110. Well, E is down here. The characters should always be what we call leaf nodes. A leaf node is right at the bottom of this branch structure, which are squares and rectangles in this case. So if E is 110, that means right is 1 and left is 0. So it can be the opposite way around, but you need to make sure either left or right has a binary code. That's how the characters are encoded, by either going left or right. So hopefully I'm doing this right. So I've labelled all of the branches with 0 being left, 1 being right. And the codes are constructed from top down. You find the letter and read off what it is. So E is 110. Z, it said, was, where is Z? Down here, 0, 1, 0. Okay, that's how you understand a tree, and it'll give you an idea if it's 1 is right, 0 is left. It could be swapped. And we've got to fill in these codes for O, I believe that is, space, and B. Right, let's just cheat and put that so I can see both at once. Ideally, if they're being kind, they'll put it so you can see both pages if it's in a booklet. So I believe that is in O. So therefore it is down bottom right. So you've got to look where the character is, then read off the code from top to bottom, not bottom to top. So this one, 1, 1, 1. Space, which is a character, don't forget that, is just 1, and I forgot 1, 0 there, 1, 0. And B is at the bottom down here, so let's actually follow that down, she might make a mistake. So we've got 0, we've got 0, 1, 1, 0. Now just a quick note on those zeros at the front, you might be used to cutting off zeros at the front, because if that was a binary number, they would not be important, but actually here they are really important, because if we cut off those two zeros, B suddenly becomes E, and they're not the same clearly, so you've got to include all the zeros, don't lose any. 1.8 is a really common follow-up. This one actually is a bit more of a tame version of what you could get. So here we need to calculate how many additional bits are needed to store the same piece of text using ASCII, and it tells us that using Huffman coding, this text can be stored in 83 bits. So Huffman leads to it being stored in 83 bits. Now I said this was more tame because occasionally you'll have to actually calculate this yourself, which is a bit tedious, because what you've got to do is you have to find the code for all of the characters in this text and then effectively join it up together. Or count how many Z's there are, count how many O's there are, count how many E's there are, and multiply that by the length of your codes, add them all up to give you the total. So there's not an easy way to find this without using the tree to see how long each code is. ASCII is more straightforward because all you need to do is multiply how many characters you have in the text by 7. It's 7 because ASCII by default uses 7 bits per character. 8 bits per character is extended ASCII. It's always use 7 unless you're told otherwise. So let me just awkwardly count how many characters there are. Can't forget the zeros, so be careful. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. 26 characters. Now we've got to multiply these together. Now I can't do that in my head. I'm not going to embarrass myself doing so. Always be cautious in the exam is my tip. So 7 times 6 is 42. 2 times 7 is 14, plus 4 is 182, or gives 182. So therefore ASCII takes up 182 bits. So to calculate the additional bits needed, if it was ASCII, we just find the difference between the two. So let's subtract 83 from 182. So this is going to give us 99 bits. So ASCII would have taken up 99 more bits if it had been used, although the slight caveat is Huffman coding helps compress, but you've got to store the entire tree as well. We never really consider that when we're doing these calculations. Moving on to question 2 then. So Bob purchases a 4GB SD card for use as secondary storage in his phone. Calculate how many megabytes there are in 4GB, and we need to show you're working. You should always be on high alert when you see that, because occasionally I've seen questions where even if you put the correct answer, you can get no marks unless you show working. And of course, if you get the answer wrong, you might still get 1 mark for that. So you need to know this sequence of units, right? We have a bit as our lowest unit, it's just 0 or 1. Then we have a nibble, which hasn't really got a symbol. Then we go to byte, which is capital B, that's 8 bits or 2 nibbles. Then we go to kilobyte. Then we go to megabyte. Then we go to gigabyte and terabyte. Then you have petabytes, which are not nearly as common. Now, apart from the timesing by 8 here, we are always following a pattern of timesing by 1000. Now you might occasionally hear timesing by 1024, but 1000 is the kind of correct way to do it, I would say. Right, so therefore, if we have 4GB and we have 1000 megabytes in 1GB, we are doing 4 times 1000 megabytes, which is therefore just 4000 megabytes. So easy. Just make sure there's some working to show you have not just guessed. For 2.2, we are potentially reminded that an SD card is a type of solid state storage. State 2 advantages of solid state storage compared to magnetic storage. So magnetic storage, most commonly, is something like a hard drive. Well, SSDs, crucially, or just solid state storage more generally, just has no moving parts. That's really important. So let's say, it just says state, so we're not really explaining. So it just said no moving parts, but the idea is they're generally more durable than magnetic, because if magnetic's spinning really fast, the disk is spinning really fast, that's prone to breaking if you say dropped it. If you drop an SD card, not really a big deal because it's just a solid bit of plastic and metal. It's not really easily affected. Another benefit is these have a quieter operation. And if you really want to be clear what you mean, there's no fan and no spinning disk is why, but it doesn't actually say to explain. Right, so an SD card is one of these things, in case you haven't seen one before. Often go into cameras because they're really small and really portable, so you could say that as well. They are very easy to transport, very portable and light, and don't need as much power, etc. So there's a few things you could say, and that's true for all SSDs, really. Now it says, next question, many modern desktop computers have both solid state drives and magnetic hard disk drives. Give 2 reasons why desktop computers have a magnetic hard disk drive and a solid state drive instead of having just a solid state drive. Well, solid state drives, SSDs, are faster than hard disks, hard drives, and so that's often why we have them, right? If you want to upgrade your computer, it's a simple upgrade to put in an SSD, although a lot of computers nowadays just have SSDs. Actually, this is a little bit outdated maybe. But SSDs being faster is not that relevant because it does say you could just have an SSD. So why do people compromise and have a hard disk drive? Well, because they're cheaper. So hard drives are cheaper per gigabyte, right? It obviously is relative based on the size. And again, this is a give question, similar to state, so we haven't got to explain this, but you could explain that obviously things being cheaper is a good thing, so you could have more capacity. But also, they tend, let's actually say what I mean here, hard drives, just HDDs, tend to have a larger capacity. We can say per unit, because again, the cost is obviously tied to the capacity, but per unit, you might get, say, an 8 terabyte hard drive, whereas SSDs might only be up to a few terabytes maximum. So overall capacity can be larger, let's just say that. So speed is relevant when we're comparing, but not really for this question, because it does say you could just have an SSD. For 2.4, we need to describe how data is stored on and read from a magnetic hard drive. For 4 marks, so we're looking for 4 points here, if possible. And describe means you really take the examiner through how this works. Okay, let's just draw a really rubbish diagram of how this would look like. If you took the kind of case off a magnetic hard drive, inside you'd have usually several discs, and the discs are going to spin really, really quickly, usually about 7,000 times a minute, if not a little bit higher. And there'll be what's called a read-write head in the disk, in the case of the hard drive, which is able to, as the disk spins, go across the radius of the disk. And so we've got two moving things. We've got the disk spinning really fast, and we've got the read-write head kind of shuffling across the radius. And an optical disc, like a CD, works by having bumps and flat bits on the disk surface, and they can be either 1 or 0. A magnetic hard disk is harder to depict, but areas of the disk are in two different magnetic orientations, or two different polarities, and one polarity equals 1, one polarity equals 0. So the read-write head either magnetizes or demagnetizes parts of the disk to represent the binary, and it can detect the magnetism when it's reading it. So let's think about how we're going to structure this in a proper written answer. Let's start then with the idea that the disk is moving. So let's say the disk spins several thousand times a minute, and let's say magnetism on the disk is used to represent the binary codes. The disk, by the way, is also called a platter. So if you hear about platters, that's just another word for the disk. And disk is spelled with a K when it's magnetic, it's spelled with a C if it is optical, which is a slight weird thing. But anyway, what can we say next? So that's quite vague. That's just saying we're using binary, which of course we are. Let's now say one polarity represents 1, represents binary 1, and another represents binary 0. Now this is not quite how it works, but I think it's fine as a sort of mental model. If you can imagine a compass, you've got north, south, east and west. The polarities in which direction, which orientation this magnetism is facing, say facing north might be a 1, if it's facing east, that might be a 0. Now, not quite how it works, but that's the gist, I suppose. Now, I reckon that's 3 marks. I've done colours as I made separate points. You wouldn't in the exam, of course, but it can be useful to really think about breaking down your sentences so that each one is worth a mark. So I mentioned the disk spins, but also the read-write head spins. We haven't really mentioned how actually the data is read from it. We've said how it's stored-ish. So let's say the read-write head can move across the surface of the disk. And then let's say when it is writing, it can, what can we say? When it is writing, it can change these polarities, and when it is reading, it can detect these polarities. Okay, and that should be sufficient for 4 marks. We've made one more point that I need to make, but I think that's a fairly complete answer. Now just be really clear, when you're reading data, that means you are, say, opening a file. When you're writing data, you are actually saving a file, is essentially what those 2 words correspond to. Now, other words you might come across besides platter, which is another word for a disk, like I said, you might come across tracks, you might come across sectors, you might come across, in mark schemes, saying concentric. Those words are not important, you don't need to know those for sure, but you might see them in various places. So if I can just quickly, with another rubbish diagram, show you what these words mean. So we've got our disk, we've got our platter, and let's start with concentric. So concentric circles, where you've got multiple circles within one bigger circle. Now that's rubbish, let's pretend those are even. Each of those are tracks. So a track is just a circle within the disk. A sector is really a little chunk of the disk. So we'll have several sectors in the disk, and they're usually read in one go. So you might have a program across a sector, might be across more than one sector occasionally, but that's where those words come from. Not that important. What I've written here would be more than sufficient. Although I realise I've made a typo at the end, not doing the correct word for plural of polarities. So polarity is just another word to describe the magnetic orientation. Okay, for 2.5, we've got our extended response question. You'll get at least one of these in the paper. You can tell they are extended response questions because it will usually be a discuss question or evaluate question. Often you'll have impacts chucked in, and there'll be about 9 marks. Okay, so these are not one of your quality of written communication questions. You might get in other exams where you get a star and you've got to make sure spelling is bang on. These are not quite the same. You have got to answer these in a coherent way. You'll get marked based on levels, and so your performance is linked to your general answer, not just about how many points you make. So you've got to write this properly, it can't be in bullet points. You should really think hard about it before you start writing. I would always advocate doing a little plan so that it becomes nice and joined up. So your actual question is, in recent years, there's been a large growth in the use of cloud storage. Discuss the advantages and disadvantages of using cloud storage. It really is an evaluation question. But we should include an explanation of the reasons for the large growth in recent years and consider any legal, ethical and environmental issues related to the use of cloud storage. So there are really 3 parts to this question. We've got, first of all, the idea that we're doing pros and cons. We've got why cloud storage has really picked up. So it does say you should include reasons for the large growth in recent years. And we've also got to discuss the impacts of it on sort of wider society. So look, it's not as simple as just writing 9 points. But in my head, I'd be thinking, well, let's try and get roughly 3 marks for each of these parts to the answer. And thinking about the order here, how could you link this up? I reckon it might make most sense to start with why cloud storage is really picked up, then go to maybe individual pros and cons for individual people, then go on to the impacts. That would be, I would say, quite a rational way to approach this question. And that's what the examiner's looking for. They're looking for your answer to be fairly well reasoned and to connect up quite nicely. Now I'm doing here what I always recommend to do, which is a really quick plan. Now I'm going to spend a couple of minutes talking about this. You would ideally do this in, say, a minute or 2, just really quickly, not here. I've got the luxury of deleting it. Do it right on the side, do it on any spare paper you've got. Just don't write the plan in the actual answer. So let's actually model that a little bit and do that at the top. So what are some reasons for cloud storage really picking up? Cost is always a factor, right? I would say costs have gone down for big capacity devices. So you can now get, say, 8 terabyte hard drives, which are not too expensive. For cloud storage providers can buy lots and lots and lots of massive hard drives. It makes it more efficient for them. I also think from a user perspective, the rise of just portable devices fit really well with cloud storage, things like mobile phones and tablets, but also we've got now fast networks like 4G and increasingly 5G, which are good for when you're out and about. So those could be our reasons for why it's blown up. In terms of pros and cons, I would say big pros of cloud storage is available anywhere. But the key downside is, of course, you've got to have internet. So it's a nice way to link it. You've got to have internet at all times. Another advantage I like to talk about a lot is scalability. The idea that you can very easily increase your capacity of cloud storage because there are so many servers available and the big companies have got so much storage space. You increasing your capacity by a little bit is not going to affect them at all. Whereas if you run out of your SSD on your laptop, without cloud storage, you've got to buy a new SSD, you've got to try and hook it up. It's a bit of a pain, right? Very easy to increase how much data you're using with cloud storage. But to link back to a downside, we could talk about the fact that it's an ongoing cost. You're not paying for it once, like you would if you bought a new SSD. You pay for it every month, and it's a cost which adds up. So if I'm only looking for 3 marks for that part of the question, I don't want to write loads more. That would give us roughly 3 marks. It is a rough thing here. It's not a tick question. Now regarding impacts, let's start with environmental because I think that's maybe the easiest to mention. So it takes a lot of energy to run data centers. So data centers, let's link that to energy use. They've got to be cooled down. There's obviously lots of computers running 24/7 and lots of security systems. It takes up a lot of energy, which if it's non-renewable is bad for the environment. What else could we say about the impacts? What about ethical impacts? So ethically, how private is the data, or how private should the data be? If the government, say, suspected somebody using cloud storage to be a criminal, should the cloud storage provider give over the so-called criminal's data? Is that a privacy issue? And for legal issues, there is a, let's say, responsibility. There's a responsibility of the cloud provider to have good security. Under something like the Data Protection Act, they've got to have good security, which costs a lot of money and is a big responsibility. So look, that took me, I don't know how many minutes that took me, maybe a few minutes to talk through those. In a real exam, I would literally just scribble these down really, really quickly in shorthand, because you can read your own handwriting. I would not do this in as much detail I've done here, but I think having a quick plan is really useful, especially having an order of how you're going to write this. So let me write this right to left here, starting with reduce costs. So let's start by saying, in recent years, costs for large capacity storage devices have gone down. This has made it more affordable for cloud providers and has meant it ends up being cheaper for customers too. So let's say the growth of smartphones on high bandwidth networks like 4G and 5G for that matter. A high bandwidth network can transfer lots of data at once, and so it becomes easier to access larger files on the go. And that's, probably all I'd want to write for my reasoning for it. But I can link this quite nicely into benefits for customers. So let's switch colors to demonstrate this slight mood shift. Where can we start? What did I say in my little plan? So available anywhere, which is really convenient for customers, although perhaps users is a better word at this point actually. Why is it convenient? Well, let's say as they can access the same file from several devices. However, and let's link this to a negative point, however, you must have an internet connection to access for cloud storage. And let's say this may not be possible, especially in rural areas. Now, looking at how much space we have left, usually AQA give lots more space for these sort of answers, but they haven't here for some reason. It is a specimen after all, it's not a real exam paper, so it may not have been tested as properly. But at this point I'd be thinking, well, I need to mention environmental issues, so maybe my point about scalability is not going to fit in here. You might feel that actually it's worth focusing more on the impacts of society, not just on individual people. That's a judgment call you might have to make. Again, these questions are very much about your overall answer, not about your individual points. So let's merge into these impacts, starting with the environmental one. And let's link it by saying customers might have environmental concerns. Data centers run 24/7, and the powerful computers take up a lot of electricity and need to get cooled down. And to be really clear, while this is potentially a bad thing, let's say the source of this might be non-renewable. And then to link this to a final legal point, again, I wanted to talk about privacy a little bit, which I think, based on the space and how long this question took me to answer, I might cut out. But that's quite normal. Adapt your plan as you're going. You might think of better points. You might realize you can't fit these in when you're writing. So let's go on to security, because that's such a key problem. So let's say there is a legal responsibility to keep the user's data private or keep it secure by having adequate security measures. And let's say without these, they could get fined or sued. To be really clear about what the impact is here if there was a data breach. Now, I'm writing a little bit off the answer lines here, which is risky. Okay, so please don't ever write outside of the main box. The way these are marked is they get scanned in, and so the examiner on their screen will see just your answer. That's why writing for margins is a problem. Writing a plan is fine because I won't get marked, but the actual answer should get kept in this box. If you really, really want to write more and you have lots of points to say, and you've got time left at the end, say, ask for more paper. In fact, often these have extra paper at the end, which they don't actually here. Sometimes they do. So don't be afraid to go onto new paper if you have time, but generally use the amount of space as a guide, because I was going to write more than I needed to. Okay, so look, the colours hopefully signal how much I wrote. on each of those 3 points. When it gives you several things to write about, make sure you do write about all of them. It's really common for somebody to forget one of those things because it's such a long question and so many parts to it. So that's why planning is useful. And I've tried to use as many linking words as possible. So even things like this, link sentences together. I've used that a couple of times. It shows you're connecting things up. Using words like also, using words like however are used somewhere as well. So those sort of words are good because it shows you have actually thought hard about connecting up your points. And to get the top marks here, you need to have a logically sound answer which links and connects up these several related issues together. Okay, right, that took a long time, that question. In the real exam it should only take about sort of 11-12 minutes max. So moving on to questions on networks, it looks like. So most schools have a computer network. Some schools allow teachers to access the school network from their home computers. Give one reason why some schools allow this, and one reason why some schools do not allow this. Well, a reason for thinking about this school scenario might enable teachers to work from home. So one reason for might be teachers can work from home and access their work files. Well, what could a risk be? Well, a risk could be the idea that maybe the security on the home computers might not be as strong. So something like malware could enter the network. Okay, other reasons might be data protection. So the personal details of, say, students and other staff are really important. You'd want control over it as someone in charge of a school. So that could be a reason as well against having this access. Now, 3.2 is a more general version of 3.1, I suppose, although just on advantages. So we're going to state 3 advantages of using a computer network. So let's just bullet point this because we might as well. It's only a state question. So let's say files can be shared easily. Let's say hardware resources, e.g. printers, can be shared. And let's say communication can be done quickly. We can send an email and that's sent really, really fast. Those are the 3 most obvious ones which came to me. Things like backups you can mention, things like having central control of certain resources like software or security. Those are other advantages of networks. And PANs and LANs are 2 different types of networks. Describe one difference between a PAN and a LAN. So a PAN is a personal area network and a LAN is a local area network. Now a PAN is just for one person, so someone having, say, a Bluetooth headset would be part of a PAN, whereas a LAN is usually, say, a home network or a small business network over one building. So let's say generally you could say about the distance, that a PAN is over a very, very short area, usually just over one person, but let's just say a PAN typically only has one user. If you've got, say, wireless headphones, you're not connecting up to several other phones, it's usually one device. Now, I'm just finishing this off by being really clear that a LAN might have several. It's important for these describe a difference questions that you actually mention both things in the answer. Don't just say a PAN has got one user, because how's that different to a LAN? You've got to be really clear about the actual difference. It'd be a silly way to lose a mark for that question. And 3.4, I've got to give one example of where a PAN could be used, which I just did a couple of times inadvertently. So let's say connecting up wireless headphones to a phone. Think Bluetooth for PANs, not the only PAN network. Something like a mobile hotspot could be considered a PAN. NFC networks could be considered PANs as well. So I think Bluetooth's most obvious, but not the only one. For the next part, we are reminded that when 2 computers on a network communicate with each other, they need to use the same protocol. Define the term network protocol. Now, like the definition for algorithm in paper 1, this is a very just fixed answer you need to know because it comes up constantly. So protocol is a set of rules, that gives you 1 mark, that enable 2 devices to communicate. Now, really, they kind of gave that last bit in the question, but that's the kind of stock definition for protocols. Without a set of rules, how on earth would you have two separate devices by two separate companies ever communicate? Now, we've got some multiple choice questions here. I think our first one's actually possibly, or maybe my memory's just bad. So we need to write down a protocol for each of these scenarios or each of these descriptions. So first of all, use to retrieve email stored on a server, HTTP, HTTPS, FTP, SMTP, or IMAP. Well, the first two are for viewing content on web pages. S is our encrypted version, hypertext transfer protocol. FTP, file transfer protocol, not something you've probably used so far. You might use it if you do some research at university maybe and move stuff around from several servers. That's when I've used it only ever. That's for moving files about from different servers. And so it's between our last two, SMTP, Simple Mail Transfer Protocol, and IMAP, Internet Message Access Protocol. You've got to learn these acronyms. It takes a while to learn them, but you need to. Now, unfortunately, these two mail protocols don't tell you much. Retrieving is inbound email, so reading email. And so I think that A is access. If you are accessing something, you are retrieving it. Whereas the T here is transferring. I tend to think if you are transferring something, you are sending it. That's how I personally remember the difference. So IMAP is therefore the one where you are retrieving email. For 3.7, use to make a payment securely when purchasing goods from a website. You get the same options again. Well, I said HTTPS is our encrypted version. If a web page is encrypted, it means only you and the web server can see the content, right? It can be intercepted, but it can't be understood. So therefore, if it's secure, it is HTTPS. And for 3.8, use to send an email from a client machine to an email server. If you're sending email, based on what I said, you are transferring it. It is SMTP, Simple Mail Transfer Protocol. Okay, and TCP/IP is a protocol used in networking. Really, it's a group of protocols. TCP/IP is what the internet uses. So there are 4 layers in the TCP/IP stack. Complete the table by placing the 4 layers of this stack into order, where 1 is the top layer and 4 is the bottom layer. So I think the layers can be really confusing for students. It's not great advice, but my advice is usually don't think too much about it. The layers are just used as a way to break down and categorize aspects of the communication. So the idea being, we've got our 4 layers, and the top layer, when you want to send a message, it starts at the top layer and works its way down. So it passes through each of the layers, and the protocols which work at each layer do something to the message. So they add some data, they put it in a packet, they enable it to get transferred. And when the data is received at the other end, the packet works its way up, again through the layers, until it reaches the top one. Then you can respond to the message. So the layers are just an artificial thing computer scientists have come up with to sort of categorize aspects of this process. So the thing which starts and ends the communication is the application. So the application layer is our top layer. The application is what sends the packet. It's what receives the packet at the very end. The next step, once you're sending it, is to transport it, to transfer it. So the transport layer is our second one. It's where TCP and UDP work. You'd have either TCP or UDP, and they actually set up the connection and put it into packets. The next one is the internet layer, also called the network layer, which is where the internet protocol works. It's where an IP address will get assigned to each packet. And finally, the link layer is what, as the name would suggest, connects up the networks. So it's where the physical hardware connects up to the software. So Wi-Fi and Ethernet work at the link layer. Right now, many computers use the von Neumann architecture, the vast majority in fact. It says in a computer that uses a von Neumann architecture, bit patterns can be stored in the main memory. Shade the correct lozenge to indicate what these bit patterns could represent. So data, instructions, data and instructions, data or instructions, but not both. Well, the idea is we differentiate between data and instructions, which I think is confusing. I always seem to use the same example when explaining this. Something like 5 plus 10. Well, the data in this instruction, so really the instruction is add. The data are 5 and 10. And the instruction is just the add operation. So if this was, say, machine code, not machine code, if this was, say, assembly code, it might be like add 5, comma 10, right? So that's the difference between data and instructions in this context. It does seem odd because anything can be data, but it's got a particular meaning in this context. So the point is, von Neumann can have both data and instructions, and they're stored together in the same memory unit. An alternative is having them in separate bits of memory, so having the data in one and the instructions in the other. That's called the Harvard model, and it's just a different approach, which is not used, at least on the surface, as often. Now for 4.2, we're given 5 components of a CPU, and we need to match up these components to a description of them. So our 5 components are bus, ALU, arithmetic logic unit, control unit, clock, and register. So the first description is sends a continuous series of electronic pulses. Now that is going to be between either A or D, a bus or a clock. So if we've got our CPU, and if we've got, say, our motherboard, which is much bigger, but I'm not going to draw it properly. CPU is on the motherboard, it slots into a socket on the motherboard. There'll be a clock in the motherboard, and a clock is just often a little crystal which produces a really, really steady, continuous pulse. And the clock is used to synchronize circuits. If all of the circuits are based on this steady, reliable, continuous pulse, it means things can work together and there are not conflicting operations done at once. And the clock on the motherboard will be connected up to the CPU via a bus, and there'll be another clock in the CPU which is often a lot faster than the motherboard one. So sends a continuous series of electronic pulses. The bus will be actually carrying this series of pulses, but it's actually being sent by the clock, and the clock is what is producing this series of electronic pulses. Therefore the letter is D here. Now, but it's a bit ambiguous, that statement, but I'd lean more towards D for that one. The other two are more straightforward, looks like. So the next one, decoding the current instruction. If you are decoding an instruction, that means you are interpreting it. This is done during the decode stage, funnily enough, of the fetch, decode, execute cycle. And by decoding, we might get, say, during fetch, we might get something like this, a binary code. In decode, it's got to figure out actually what you are doing. So let's say that is the add instruction, and let's say you've got to get 2 more bits of data during execute. So decode is kind of getting ready for the next step, figuring out what you need to do. And that is done by the unit which controls this whole process, which is the control unit. And the last statement is completes calculations, short and sweet. This is the arithmetic logic unit. So that does maths operations and also logic operations. It's where the actual instruction, like addition, gets carried out. Now for question 5, let's start moving on to cybersecurity. So social engineering is where someone is tricked or manipulated into providing secure information or access to a secure system. Describe each of the following social engineering techniques, only for 3 marks. So it's odd to have a describe question which is so brief. Usually you'd get, say, 2 marks per area to discuss or describe here, but no matter, really, it's a state question. So blagging is where you make up a fake scenario to try and access some information. I've added all money because it could just be a trick to get some money directly. And if this was worth 6 marks, which I think feasibly it could be, you could then give an example, e.g. impersonating a police officer to try and obtain somebody's address. Something along those lines is blagging. Now phishing is where a fraudulent message is sent which tries to trick the victim into responding to it. Now, it's only worth 1 mark this part of the question, but just to be really obvious, you might say, e.g., an email with a disguised link. So they're not always emails, but they are a lot of the time. People often say a fake email. I think a fraudulent email, a fraudulent message is better because it is a real email or a real message, but it's just committing fraud, right? And the final one, shouldering, is probably our easiest one to understand. This is where somebody looks over somebody's shoulder to observe them entering some personal information. And if it was worth more marks, you could give an example, somebody looking at somebody entering their PIN at a supermarket checkout. Something along those lines would be an example of shouldering. Okay, now for question 6, going back to data rep, looking at sound now, which I always really like as a topic, but it's one I think people find difficult on occasion, so it's worth focusing on as you're revising, I would suggest. So a sound engineer is recording a singer. Describe why the sound must be converted to a digital format before it can be stored on a computer system. For 2 marks here, so a more typical describe question. Well, we have 2 types of information formats. We have digital formats and we have analog formats. Now as I'm speaking in real life right now, I am speaking in analog because the sound waves are continuous and I could go as loud or as quiet as my voice box would allow. It's a continuous smooth range. There are an infinite number of volumes I could theoretically speak in because it's a naturally occurring signal. Whereas digital has to be discrete, has to be finite, it has to be within a set number of values. And so my microphone in front of me is converting my audio in analog to be this discrete, finite digital data. So let's say natural sound or natural spoken sound is analog, which is continuous. Computers can't represent this in binary unless it is converted to discrete digital data. The next part is a very typical question again, which you'll get a similar one for images as well. So working out the file size given a few different values. So the sound engineer is using a sampling rate of 2000 Hertz. I tried to highlight that properly. A sample resolution of 4 bits, and it is 5 seconds long. That is our key information because the formula is for sound is always rate times resolution times how long it is, so the seconds. And we must also give it in bytes. We can't forget that here. It's worth 4 marks, quite a generous question because there's no rearranging. You might occasionally have to rearrange it if you're missing one of these variables. But that's just algebra, which you should be able to do from maths. Okay, first of all, sample resolution is for one of people find hardest to get their heads around, partly because the word resolution is unfortunately also used for images. Now, image resolution, I find people are quite good at understanding, but not so much in the context of sound. So in the context of sound, we can imagine our sound wave on a graph. If our x-axis is time, so as time goes on, the sound wave does this. The y-axis is the distance or the displacement or the height of your wave. And the sample resolution determines how many possible values you can have on the y-axis. So with a sample resolution of 4, you've got 2 to the power 4 possible combinations of volume. So the volume is dictated by the sample resolution, but indirectly. 2 to the power 4 is 16, so there's 16 possible volumes in this example. What that means in practice is, the y-axis would be labelled something like this: 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, all the way up to 15 at the top, which is just 4 ones. And as you're taking samples, you go along the x-axis, read across at set time intervals, and it has to correspond to the nearest volume. And how often we're doing it is a sampling rate. So here we've got a sampling rate of 2000, it means we're taking 2000 samples per second. That's what that means. Anyway, that was not particularly relevant for this particular question, but I wanted to give a quick recap there. because all we're doing here is just plugging in these numbers to this formula. So first of all, our rate is 2000, our resolution is 4. The resolution is always in terms of bits. It's similar to the color depth of images, and this is a 5-second recording. Now let's do 4 times 5 first, which is 20. So I'm really doing 2000 times 20. Now 2000 times 2 is 4000 times 10 is 40,000. So this is 40,000 bits, but we've got to put it in bytes. So to get it in bytes, we divide 40,000 by 8, which is going to be 5,000 bytes, which is our final answer for that question. For 6.3, we've got a question which I think just repeats what I just talked about. So a sound engineer currently has a sample resolution of 4 bits, which enables the sample to be stored as one of 16 different bit patterns. I did say that. She wants to increase the number of bit patterns available from 16 to 32. Shade one lozenge which shows the minimum sample resolution she can choose, which will allow her to do this. So really here we're going, well, 2 to the power x equals 32, or which is nearest to 32. Well, there is a direct one here. If x is 5, we're going to get 32. So therefore we're looking for 5 bits as our sample resolution. As a general rule, if you're looking for combinations of binary, you're always doing 2 to power the number of bits you've got. That's how the combinations work in lots of areas. So for color depth as well, for the number of rows in a truth table, how many characters ASCII can encode with 7 bits. This all comes from this really simple expression. So therefore the answer here is B. And just before moving on, let's say hypothetically this question was, okay, she wants to increase it to 37 possible bit patterns. 37 volumes need to get represented. What would be your minimum sample resolution? Well, again, you're looking for, well, 2 to the power x equals 37. The issue here is there isn't an exact answer, which is an integer. You could probably go 5 point something, 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 but it needs to be a whole number because we're dealing with a whole number of binary digits. So you're looking for, well, what would give us above 37? Well, x equals 6 is our next one up, because 2 to the power 6 is 64. Now 64 combinations is bigger than 37, but because you're between the exact numbers, you've always got to go one bigger. So if it was 37, the answer would be 6 bits, not 5 bits. You always go to the next one up. Okay, for 6.4, we need to shade one lozenge to show which of the following correctly states the effects of increasing the sampling rate. Well, if you increase the sampling rate, you're taking more samples per second, so the file size will increase because every sample has to get converted to binary and be stored, but also the quality of the recording becomes closer to the original analog signal, and so the quality generally will go up. So quality goes up, but so will the file size. So there's a trade-off between quality and file size. Now, as we head towards the end of this paper, I've got a couple of questions left, I believe. We're now given 3 examples of code which we're told are all equivalent to each other, and we've got to answer, just one question here on this code. So, which of these statements is true? None of the examples are in a low-level language, only one is, only 2 are, and all 3 are in low-level languages. So, we've got this dichotomy between high-level languages and low-level. Something like Python is high-level, something like assembly and machine code are the 2 main low-level languages. Now, the high and low refers to abstraction. I can recall feeling very smug when I learnt Python, learning it was a high-level language. I felt very intelligent. It's not about how hard it is. In fact, you could argue a high-level language is easier than a low-level one. It's about the abstraction. How much simplification is there between what you're doing on the screen versus what's going on within the computer. Something like machine code, which is example 3, is as close as you're going to get to what the computer's doing, because 1 is something being on, 0 is something being off. Whereas say Python code, which this is pseudocode but similar enough, is high level because it's not really what the computer's doing. It has to get converted to machine code. And in the middle we've got assembly code. Assembly code is low level as well. but it's closer to machine code. There's a one-to-one connection between machine code and assembly code, meaning one assembly instruction equals one machine code instruction, whereas one Python instruction, like A equals 4, might be several machine code instructions. So in essence here, we've got two low-level languages, which is lozenge C. Example 1 is pseudocode, but that's not low-level. It's not high-level either, you could argue, but it's definitely not low-level. That's only assembly and machine code. For question 7.2, we need to explain why a developer who is good at both low-level and high-level programming would normally use high-level languages when writing programs. And it's worth 4 marks here, and it doesn't give us a limit on how many reasons we can give. So let's aim to give 4 reasons here, just to be on the safe side. Well, the idea is, well, one of the key aspects is high level is more like normal English. So it is easier to understand and quicker to write. You know, the assembly code has parts of it which are in English, like mov, you can probably tell is move. CMP is probably compare. I think B&E is branch, if not equal. So it is English-ish, but their mnemonics, you've got to remember what these stand for. They're not nearly as helpful as something like an if statement or while loop, which actually tells you what it's doing. Let's also say, because of the readability, bugs are easier to find, or are often easier to find. I can't tell you how many hours I spent at university hunched over an assembly program in the late night, trying to understand how it was working and try and get bugs to get fixed. It can be tricky because a lot of it blurs together. Although, to be fair, that also applies to high-level code as well. Now, what else can we say? Well, high-level languages are portable. Let's say they are also portable. Now, something being portable means you can take it about, of course, but in the context of a program, being portable means it can run on several computers. Why is that a good thing? Well, meaning the developer does not have to rewrite code for different CPUs. Now, I said assembly is one-to-one to machine code. Well, machine code is specific to the CPU's instruction set, and different models of CPU and even different versions of CPU have different instruction sets, and so the assembly code is specific to that one instruction set. I think often it's taught as if there is just one assembly language called assembly code. That's not the case. There are loads which are just specific to particular processors. Whereas Python code can run in all processors because the different translators convert it to the different machine codes. And let's make a final point. The high-level languages tend to have more support online because they've got more developers. If you're programming for quite a niche CPU, the assembly code might not have much documentation, which again makes things a little bit harder. So there are some reasons. Now, the benefit of writing either assembly code or machine code is because they're much closer to what's going on, they are faster. So they're faster to execute, and you can often do certain efficiency boosting things using assembly and machine code in particular because you can optimize it a bit more easily. Now, writing machine code is almost impossible, I would say, apart from if you're, say, developing a language from absolute beginnings. Assembly is hard, but if you were writing for, say, an embedded system, you might find that actually that increase in speed is worth it. Now, I mentioned translation a couple of times. Maybe I didn't say what that is. Translation is when you convert instructions from one programming language to another. So, for example, converting from high level to machine code. And statements A and B refer to two different types of these translators. We've got 3. We've got compilers, interpreters, and assemblers. So the first one, this type of translator can convert a high-level language program into machine code. And the source code is analysed fully during the translation process. The result of this translation can be saved, meaning the translation process does not need to be repeated. And statement B, this type of translator was used to convert the code in example 2 to the code in example 3 in figure 4. Well, I've said a few times, example 2 is assembly and example 3 is machine code. So therefore, statement B is easier. Statement B is an assembler. An assembler is the only translator which goes from assembly code to machine code. Compilers and interpreters only go from high level direct to machine code. So statement A is really asking us, is it a compiler or an interpreter? Well, a compiler will look at the entire code in one go and spit out a .exe file or equivalent, a file which you can run to execute the code. An interpreter will go line by line and run each line directly after executing it. And if you want to rerun the program, you've got to translate it all again line by line. So statement A is actually a nice definition of a nice description of what a compiler does. So that bit about enabling it to be saved is really saying, well, it can produce an executable file, which an interpreter can't. On occasion, there'll be a long question on compilers versus interpreters. Compilers are beneficial in the sense they're quite fast, they're quite efficient because they can optimize. During that analysis at the start, it can look at the entire source code and do various little tricks to make things faster. For example, it can replace constants with the actual values. It can put short subroutines inline. It can do little tricks to make things faster, which an interpreter can't do. Because an interpreter can't see the entire code, it can't do those optimizations. A compiler will also produce this file, which you can send people. All you need to send is this file, not the actual source code. So your source code can be kept private because this file is just in binary. An interpreter, if you want to send the program to somebody else, you've got to send both the interpreter and the source code, so it's less private. But an interpreter is good for testing because once you hit an error, the interpreter will stop and you can fix the error. I've spent a while occasionally compiling programs only for 10 minutes later an error to occur, and it's a waste of time because it only tells you there's an error right at the very end or when you try and run the code. So it's good when you're done, but not so much when you are writing it and encountering errors. Okay, and now we've got Boolean logic questions. So we've got to complete the truth table for the AND logic gate. The truth table shows you the combinations of different inputs. And here, first of all, 0 and 0 is 0. For AND to be true, both sides, both variables have to be true. So a 1, in other words. So 0 and 1 is also 0. 1 and 0 is also 0, but 1 and 1 is 1. Now, we've now got to do a logic circuit. Just quickly on the other gates you've got to know about. You've got to know about OR. So OR is where you would have 0, 1, 1, 1. So where one side can be, let's put this here, where one side needs to be true. XOR is where exactly one side has to be true. So it's a little bit different. When you've got two ones, it's also 0, or at least a 0, and NOT just flips 0 to 1 and 1 to 0. So let's look at this scenario. So a logic circuit is being developed for an audio advert in a shop that plays automatically if a customer is detected nearby. It has two sensors, A1 and A2, that detect if a customer is near. The audio plays if either of these sensors is activated. So I would be highlighting this because either suggests either OR or XOR. Likewise, if there's an OR an AND in these sentences. So the system should only play if another audio system is not playing, or not for that matter. The output from the circuit for whether the output should play or not, for whether the advert should play or not, is Q. So the letters are variables, are representing the zeros or the ones. So let's have a think about this. First of all, I've got A1 and A2. It plays if either of these sensors is activated. So I said it's either OR or XOR. Now, would XOR make sense, right? If you had two sensors and both sensors were activated, they detected somebody, would that give 0? No, it'd probably give 1. 1 would probably be that it's been activated, 0 would be it's not been activated. So this one should be OR, because if both are on, if both sensors are alerting, you should still alert. So let's put an OR gate in front of these. An OR gate's the one I find hardest to draw, but it's got this curved sort of crescent moon shape at the back. And let's connect up our two inputs to it, A2 and A1. Okay, the next one, the system should only play if another audio system S is not playing. So we're going to if S is playing, S will be 1. We want S to be 0. So let's add a NOT gate in front of S. A NOT gate is a triangle with a tiny circle in the front of it, don't forget that. And a NOT gate only has one input, so let's stick that in like that. And now, how are we going to connect up these two outputs so it merges into one output for Q? Well, audio plays if either of the sensors is activated, and should only play if another audio system S is not playing. So I think we need to add this to an AND gate. An AND gate, unlike OR, has a flat side, and our two inputs are going to connect up to this AND gate. So before I would move on, I would think about, does this fit the scenario? Okay, so A1 being a 1, A2 being a 0, let's say one sensor has been activated. Okay, 1 or 0 is 1. Let's say the audio system is not playing, so S will be 0 if it's not playing. Well, then NOT would turn it into 1, and now we've got 1 and 1, which would be 1, and so Q would play, so it would play the advert. Does that make sense? Yes, well if someone's near a sensor, it says they should play the advert. Let's try a different one. Let's say we have got both sensors activated. Let's say we've got two people in the shop and they're both activating it. But let's say the other audio system is playing, so that's a 1. Well, therefore this would become a 0 out of NOT. 1 or 1 is 1, but 1 and 0 is 0, and so the output wouldn't play, the advert wouldn't play, which is correct. So test your circuit before moving on if you've got time, because you might find that you've made a tiny mistake, but it should match up to the scenario. I would just, if you have workings out, just delete these before you move on. You should be doing these in pencil. I should have said that earlier. Make sure any diagrams are done in pencil, because you're bound to invite a mistake if you do it in pen. And question 9, we've got a question on databases, which you're going to get in every paper from now on. I would say I've heard people hope they're going to avoid it, but I think there's always going to be at least one on databases, because you have to do some practical stuff in this paper, and this is the only practical topic, you could argue. So we've got a relational database being developed to store information about the games that are available to play at a games cafe and the advanced bookings that have been made for those games. Each game has a unique name. That could be important because that could be our primary key. It has two tables called game and booking. The database is currently being tested by the person who has developed it, so the database tables only contain a small amount of data that is being used for testing. And we've got the two tables shown here. Now, just on the database terminology, in both tables, is that right? In both tables, no. I was going to say in both tables we've got 5 fields, but we don't. Game has got 5 fields, and booking has got 1, 2, 3, 4, 5, 6 fields. The fields are the columns of the tables, and records are the rows. So game has got 5 rows, so 5 records, and booking has got actually 5 as well. I don't know if that's going to get asked about, but I just want to make sure those words are clear. Field column, record row. We need to first of all state the field in the booking table that is a foreign key. So a foreign key links up two tables together. That's why it's a relational database. A relational one links up two tables. So a foreign key is a primary key of another table. So we want to look first of all, actually not at booking, we want to look at game. So what is the primary key of game? Which field is unique? Well, I was going to look to see if all of the fields are unique, but actually it's told us already, name is unique. All of the games have got different names, so therefore name is our primary key. A primary key must be unique. It identifies each record uniquely. So we're looking for name appearing in booking, which it does. So therefore the foreign key is name, because name is a primary key of another table. So let's call this, or let's write down that it's called name. For number 2, we need to state the most suitable data type to use for the complexity field. Data types are really a paper 1 topic, but it's fine to bring it up here because they're the same. So you've got reals, you've got integers, you've got strings. So complexity is a decimal number. So let's say this is a real. For 9.3, we've got a 6 marker on writing a long SQL query, which could be quite daunting, but actually these are not nearly as bad once you've learned the syntax. So due to a change in layout of a cafe, the game table with an ID of 2 is no longer suitable for games that can have more than 4 players. The manager needs to find out the customer, date and time of all bookings made for the game table with an ID of 2 that are for a game that can have more than 4 players. Okay, so that's not daunting, and then I read out a very, very complicated scenario. Let's break this down a little bit. So, first of all, it does say, write a query that can be used to find this information for the manager. It will be shown in date order. So, this is select. We're looking for a select query. Now, let me tell you what told that to me. Well, we're looking for information for them. So, we are retrieving information, which is select, but also things like finding out. If you're finding out information, you are using a select query. You are retrieving data. So, we are, first of all, looking for what fields. What fields are we looking for? Because the first part of select is listing the fields you want returned. So we want to find the customer, date and time. So let's look for this. We've got customer, date and start time. So those are our 3 fields. So customer, date, start time. So all I do is list these after I write select, usually in capital letters. So in fact, not customers, customer. Make sure it matches correctly. So it's not just time, it's start time. And you might occasionally see, say, the table name, dot, the field name. But that's only needed when you've got duplicate fields, and here these are all only in the second table. So what tables are we selecting this from? So we are going from both tables. Now, these fields are only in the booking table, but I've got a list game as well, because we are about to connect up these tables using the ID field. Now we're looking to actually filter these. We're not looking for every customer, date and start time. We're looking for only those where we've got an ID of 2 for a game that can have more than 4 players. So what fields correspond to those 2 things? Well, we've got game table ID. Let's scribble that one down just to the side. But also can have more than 4 players. It's going to be max players. Now max players is in the game table. So what we need to do is filter when max players is greater than 4. What this scenario is effectively saying is, because the cafe's changed a little bit, the game table, the actual physical table, I assume, in this cafe, can no longer handle more than 4 players. And so we're looking for just the ones where it's booked the table labeled 2 and currently allows more than 5 players, or more than 4 players, sorry. So, what I'm looking to do, first of all, is filter based on the ID being 2. So let's do this now. We use a where clause for this. You don't need it always, but you need it when you're actually filtering the data. So where game table ID equals 2 is my first criteria to look for. Game table ID equals 2. Let's just double check I've done that properly. I'm paranoid I'm not capitalizing it properly, but I have. Although, yeah, I have. Now, that's not it, right? We're also filtering based on having more than 4 players. So, to stick multiple criteria together, we don't add more than one where clause. We just stick some Boolean ands together. Okay, Boolean ands where you need both things to be true. Boolean or is where either can be true. Here we want both to be true. So and, what was it called again? Max players is greater than 4. Now, it shouldn't be greater than and equal to, because if it has got 4 players, that's not what more is suggesting, right? More than 4 players suggests 5 plus. If it said that can have 4 players or more, sure, it'd be greater than or equal to, but here it's just greater than, okay? But are we done? No, because game table ID is in booking, max players though is in game. And so to connect up the 2 tables, we've got to link our foreign key to our primary key. Without that information, it wouldn't be able to correctly give you the relevant records. So whenever you're getting data from multiple tables, you've got to remember to add a where clause which has a criteria which links the primary key to your foreign key. So the way this works is, first of all, I've got to stick another AND operator. You can have many of these if you need to. And we're going to use our first table, which again, I keep forgetting the names here, is game. And we said the primary key was name, so game.name. And this has got to equal booking.name, which is our foreign key. So without this criteria, it's not able to match up the records from game with the records from booking. So whenever we have two tables, we always have a line like this, where we link the primary key to the foreign key. Now when you have two tables with the same name, which unhelpfully is called name here, you've got to give the name of the table before the field name. So when you have something dot something else, the thing before the dot is the table name, then the thing after the dot is your field name. So because I've got two names, I've got to tell it which table I'm looking for. Here we're just linking the two keys together. But if you had, say, one of your, I suppose, ordinary fields, which had the same name across two tables, again, you can be, something like game.customer, booking.customer. That's a way to tell the system which field you're looking for. Okay, the final thing we need to do is, let me try, I can't believe it highlighting. The final thing we need to do is order by date. Okay, so it doesn't say which way to order it, so we can just go order, and the thing people forget is order by is for syntax, order by, and we say the field we're sorting based on, which is date here. Okay, now you might have ascending, descending. Because it doesn't say ascending or descending, we can just leave that blank. That should be fine. Okay, now moving on to another SQL question. So the length of game field shows the average amount of time it takes to play a game in minutes. A query to add 10 minutes to the length of time taken for all games that have a complexity of more than 3 is shown here. It contains 2 errors. Refine the query to correct the errors. So refine is a keyword, meaning we are changing it to make it better. Right, so we're adding 10 minutes to just the records with a complexity of more than 3. Okay, well, first of all, more than 3, I'm spotting a less than or equal to sign. So again, like the previous question, more than means that we need to have a greater than sign and not greater than or equal to. So that's one error we're going to have to fix. What is the issue? Well, it says to add 10 minutes, and we've got a 9 here. So update our table. We're setting length of game to be length of game plus 9. It should be plus 10. Right, the rest of this is fine, just those 2 problems. So let me copy that out again. Okay, there we go. So the 2 errors should be fixed. I would say, it's such a common mistake mixing up your less thans and greater than signs. If you ever have code, either Python code, say, or SQL code, and it says to spot an error, I'd be looking for things like those signs being wrong. Okay, now final couple of questions on security. So the Games Cafe is evaluating the security for their network. State 2 reasons why using a biometric authentication measure is better than password authentication for staff accounts. So biometrics are measures of our human characteristics, things like our fingerprints, things like our voice, things like our face if it's facial recognition, say. And authentication is finding out whether someone is who they say they are. So a good reason is you can't forget your biometric measure. You can't forget your fingerprint, right? You'll always got it with you. So no risk of forgotten passwords. It does say state here, so I don't need to explain that. And let's also say things like, no risk of being shouldered, which is where someone looks over your shoulder to watch you enter your password, shouldered when using biometrics, right? If someone sees you use your fingerprint scanner, well, fine, that's not really a problem. Whereas if someone sees you enter your password, they could pick it up and use it later. Now you could talk about uniqueness. I think that's that's one of the key benefits of biometrics are the uniqueness, but it's harder to say in an exam question or an exam answer. I think because biometrics are usually unique, not always unique, right? Something like our facial structure can be similar enough that it can trigger, say, somebody else's Face ID, say. And of course, you've got people like identical twins who it wouldn't work as well with for certain biometrics. So you could mention things about it being harder to forge and harder to guess, or impossible to guess in certain cases, but it requires a little bit of a longer answer, I would say. Okay, and the final question, which is always a nice feeling. Well, it's usually a nice feeling if you are good for time. So explain why it would not be appropriate for the cafe to use MAC address filtering on their wireless network. Well, a MAC address is a identifier which every network adapter has to have, right? So your computer now, if you're watching this video, has got a network adapter. It's how it can connect to a network. It has a MAC address which is unique to that device. And MAC address filtering is where you either allow or ban certain MAC addresses. Well, this is a cafe with lots of customers, presumably, so if they've got lots of customers wanting to join their network, it's not practical to find out all of the MAC addresses and either ban or allow them. So let's say they may have lots of customers. It would be hard to find out the MAC addresses of every customer, and would be time consuming to add this to the filter or add these to the filter. And I think that's probably sufficient for 2 marks. You could mention things like, well, MAC addresses can be forged on occasion. So say a hacker found out one of the customers, they might be able to forge their MAC address and join the network from outside, something like that. Now, MAC address filtering is generally not the most effective security measure because of things like forgery. But if it was going to be used, it would be used in a very limited network. If you knew you were only going to have 5 devices connected, that's feasible to whitelist 5 devices. But for lots of public places, it just becomes too much of a faff. To have to find out every MAC address and add it to the filter doesn't really make much sense. Okay, and that was the paper done. Really well done if you managed to watch most, if not all of this video. That is impressive. And hopefully you tried these yourself and agree with what my answers are. But of course you might have some different answers. So paper 2, at this point, if you say have 10 minutes left or 15 minutes left, go back through and check every answer. Even if you are confident or very unconfident, still check. Every person makes mistakes. You might well find it if you are having time to check through the answers, okay? Now, what I used to do is add a little asterisk. If I found a question hard, I'd add a little asterisk and come back to it later. So at this point, I'd usually have a few questions to come back to once I finish it. So, make sure you attempt every question unless you are desperately out of time, right? Because you can often pick up marks for working or just simple points. Okay, so paper 2, just a case of you really, really thoroughly going through all of the content in it. Maybe things like SQL and maybe things about high level and low level languages might catch you out unless you were aware they are in paper 2 and not in paper 1. Okay, so when you do this exam, I really hope it goes well, and thank you very much for watching.